Do you know what the true boundary of our solar system is? If you thought of Pluto or maybe Neptune, prepare to be surprised. Our planetary system extends much, much farther than you could imagine. We're talking about distances so immense that even light takes more than a year to cross them. Welcome to the realm of the Oort Cloud, the most remote and mysterious region of our corner of the universe. No human has ever seen it, yet it exists. Today, we'll discover it by exploring its strangest characteristics. Just a moment, guys. Only 13% of subscribers know when we publish new videos. Make sure you subscribe and turn on the notification bell, because without it, you'll miss formats and documentaries you won't find anywhere else. It's just a hypothesis. The Netherlands, post-war era, year 1950. A Dutch astronomer named Jan Hendrik Oort, already famous for his studies on the rotation of the Milky Way, was pondering a mystery that had fascinated astronomers for centuries. Where do comets come from? Truly enigmatic objects. They appear out of nowhere, cross the sky with their spectacular tails, orbit the sun, and then return to where they came from. Some reappear regularly in our neighborhood, like Halley's Comet every 76 years. But others have orbits so long that they take thousands, sometimes millions of years to complete. Where do they stay in the meantime? Where do they hide when we don't see them? Oort examined the orbits of these long-period comets and noticed something strange. They seemed to come from every direction in space. There was no preferred direction. It was as if there existed a kind of spherical shell around the solar system, a gigantic reservoir of icy objects waiting, uniformly distributed all around us. And so the theory of the quasi-spherical cloud surrounding the solar system was born. A hypothesis based on mathematical calculations, indirect observations, and brilliant scientific intuition. Jan Oort couldn't see that cloud with any telescope of his time, and actually we can't see it even today, but he understood that it had to be there. It was the only way to explain what we were seeing in the skies. We don't know if it exists, but we have its profile. And here we are at the first great paradox of the Oort Cloud. After more than 70 years since its theorization, we still have never observed it directly, not even with Hubble or the James Webb Space Telescope. Yet, we know it's there, where it's located, what shape it has, how much mass it contains. How is this possible? The trick lies in the comets. When a comet appears, astronomers calculate the parameters of its orbit, and this allows them to determine its period, distance at aphelion and perihelion, etc. In 1950, Oort analyzed 19 long-period comets and noticed that almost all of them had their farthest point from the Sun, the aphelion, around 20,000 to 50,000 AU. Obviously, you already know that an astronomical unit, or AU, is the average distance between Earth and the Sun, equal to about 93 million miles or 150 million kilometers, and that the distance of the farthest known planet, Neptune, is only 30 AU. So try to imagine what distances we're talking about. In the following years, after examining thousands of comets, other astronomers hypothesized more precisely that the sphere could even extend up to 100,000 or even 200,000 AU. But the spherical shape? How did we figure out that the cloud is a kind of sphere and not a disk like the asteroid belt or the Kuiper belt, for example? We already said it, by looking at where the comets come from. They arrive from all directions in the sky, from above, below, from every angle. If the origin were a flattened disk, we would see them arriving only from a narrow band. Obviously, the boundaries, both internal and external, of this gigantic cloud are not sharp like those of a real sphere, but very, very blurred. And how did we determine the number of objects that populate it? Well, statistically. We know how many new comets arrive each year and how long they take to reach the inner solar system. Through computer simulations that reconstruct billions of years of orbital evolution, we can calculate how many objects must be in the cloud to produce the observed arrival rate. The result? About 2 trillion frozen cometary nuclei. The Oort Cloud is there, reconstructed piece by piece from the traces left by comets. It's the kingdom of cometary nuclei. Now, what's in this cloud? What fills this enormous space? Who are the inhabitants of this cosmic periphery? Icy objects, trillions and trillions of icy objects. Primordial comets, cometary nuclei, blocks of ice and rock floating in the absolute darkness, in the most extreme cold imaginable. They are the remains, the debris, the crumbs from the formation of our solar system, hurled out there 4.6 billion years ago by the gravitational perturbations of the giant planets. How did they end up there? Good question. When the solar system was forming, there was a disk of material floating around the proto-sun. From this disk, the planets, asteroids, moons, and comets formed. But not all the material was incorporated. Many objects had close encounters with the forming giant planets, Jupiter, Saturn, Uranus, Neptune, and were literally catapulted outward by gravitational slingshot effects. According to the most accepted estimates, there could be up to 2 trillion objects with a diameter greater than half a mile or 1 kilometer, 2 million millions, and probably billions, perhaps trillions of other smaller objects, boulders, fragments, ice blocks the size of a house, a car, a refrigerator. Each of them orbits slowly, very slowly around the sun, taking millions of years to complete a single revolution. They are dormant, frozen, motionless. They float in absolute darkness, illuminated only by the extremely faint light of the stars. Every now and then something disturbs their sleep. A star passing too close, a gravitational tide wave from the galaxy, a random perturbation, and one of them begins a very long journey toward the inner solar system, toward the planets, toward the sun, towards us. It's an almost empty box. Here's the final paradox, the one that makes the Oort Cloud even more fascinating and strange. It's immense, but empty. It contains trillions of objects, but has a relatively small total mass. It's a colossus made almost entirely of nothing. The volume of the cloud is literally unimaginable. If we calculated all the space it occupies, all the emptiness between one object and another, we could fit billions and billions of solar systems like ours inside it. Volume is proportional to the cube of the radius. So when you increase the radius by a factor of 100,000, from 1 AU to 100,000 AU, the volume increases by a factor of, well, 1 million billion, a 1 followed by 18 zeros. Yet, all the mass contained in this colossal volume, all those trillions of objects put together, equals only a few Earth masses. Some estimates say about 5 Earth masses, others say 3, still others go up to 40. But even in the most generous case, we're talking about a handful of terrestrial planets dispersed into space that could contain billions of solar systems. If you were inside it, what would you see? Probably nothing. Absolute blackness dotted only by the faint lights of the stars. The nearest objects could be millions, perhaps billions of miles away. You could cross the Oort Cloud from top to bottom, from one end to the other, and never, not even once, see one of these icy objects. Not because they're not there, but because they are tremendously dispersed in space. Hey Curious Squad, before moving on, be sure to subscribe to our channel, clicking on the notification bell, and leave us a thumbs up so you don't miss out on our daily videos. It hosts the slowest objects in the solar system. Objects in the Oort Cloud move at ridiculously low speeds, about 160 to 330 feet per second, or 50 to 100 meters per second. Our Earth, by comparison, moves at more than 18 miles per second, or 30 kilometers per second. At that speed, the sun's gravity barely holds them, like an extremely thin thread stretched across the cosmic abyss. And it's precisely this slowness that makes them extremely vulnerable. When you move that slowly, a small gravitational push is enough to completely change your orbit. It's like a tightrope walker on a rope. The slightest disturbance and you fall. A star passing close to the solar system, like Alpha Centauri is doing now, can exert the small push sufficient to deflect an object moving so slowly, changing its orbit from nearly circular to extremely elongated. And so begins the long journey toward the sun, a journey that will last 2 to 5 million years. The comets we see in our skies today left the Oort Cloud when our ancestors were just coming down from the trees in Africa. They are very slow messengers from a very distant boundary pushed towards us by perturbations that occurred in remote geological epochs. After all, as we're about to see, the spherical cloud of icy bodies is not a characteristic only of our Sun. Most stars have one, and those surrounding the Sun and Alpha Centauri, twin stars, are practically touching. It reaches out to touch Alpha Centauri's cloud. If we take the intermediate estimates, let's say about 150,000 AU, the outer edge of the Oort Cloud is located halfway between us and Proxima Centauri. The nearest star to us is 4.24 light-years away, which equals about 265,000 astronomical units. This means that the clouds of the two stars continuously interact with each other, exchanging objects and materials, mutually influencing the fate of the most peripheral objects. And of this, as you probably already know, we've had proof only in recent years, when for the first time we managed to identify within the solar system 3 objects certainly coming from our cosmic neighbor. A surprising fact with immediate consequences also on our concept of life spreading through panspermia. It's not a sphere. In 2025, a group of researchers made a surprising discovery by simulating all the gravitational forces acting on the Oort Cloud: the Sun's gravity, the influence of nearby stars, and especially the galactic tide, the gravitational force of the Milky Way itself pulling in different directions. The result? The Oort Cloud is not a perfectly uniform sphere as previously thought. It has a spiral arm structure, like a mini galaxy. Imagine, looking from above, the cloud would have an appearance similar to the Milky Way, with arms wrapping in a spiral. But what is this galactic tide? Think of how the moon creates Earth's tides by attracting the ocean water towards itself. Similarly, the mass of the Milky Way, about 1,500 billion times that of the Sun, exerts a force that acts slightly differently on different parts of the Oort Cloud, with the side closer to the galactic center being attracted a bit more strongly than the opposite side. This tiny difference, summed over billions of years, has sculpted the cloud, giving it this complex structure. It's no longer just a static sphere, it's a dynamic object, shaped by the titanic forces of the galaxy that contains us. It's like discovering that the boundary of our cosmic home is not a simple wall, but a complex architectural structure designed by the gravity of the entire universe around us. Okay guys, this is where we really live, inside a cosmic bubble that extends for light years, inhabited by trillions of ghost comets that no one has ever seen, in a region so remote that even our fastest probes will take millennia to cross it. Is there anything that particularly impressed you in this overview of correct interpretations of the laws of the cosmos? Is there anything you found unconvincing and would like clarification on? And is there anything that particularly impressed you among everything we've told you? If so, let us know in the comments. And if you want to learn more about the Oort Cloud, take a look at the complete series we have dedicated to it. In any case, don't miss the second episode dedicated to the most curious features of the cloud, currently in preparation.